Okay, then now we talk about the transient analysis. Okay, transient analysis takes place when something change. Okay, if something change, we call the transient state. Okay, I think you will learn some control theory, maybe in your curriculum. I'm not sure. And when something change, we call transient state. For example, if we have the current, maybe the current flow in the system, or the system maybe we have something change, right? If something change, the current will change, and then it will come back to the normal state. Here, this we call this period is transient. And after some time it's come to steady, we call this state as steady state. Okay. So when we analyze transient state, we will talk about the rate of change, right? d by dt will be there. Something change in according to the time. Okay, we get d by dt. And when it's steady, when it's the same value for a long time, we can use phasor or we can it's DC system, it's no problem. Okay, for transient analysis, we will learn only DC transient and DC steady state. Okay. Okay. And transient analysis is come only when we have storage device L and C. Okay, this will react to the system. Okay. As I talked in earlier, if we have the capacitor, right? The capacitor. Yes, minus. If we connect the circuit for a long time, the capacitor will get full charge, right? Full charge, and it's become open circuit. This is steady state for DC system. So if we supply DC voltage to the capacitor, it will act like open circuit, right? No current flow anymore. After the full charge, okay. After the long time, yeah. After long time. After long time. Full charges. Okay, it's become full charges. But when we switching on, during switching on, we will close the switch at t equal to 0. Here. The voltage across the capacitor, current flow is there. Okay. The voltage will be come to some value, right? So after full charge, this voltage is equal to the voltage of the DC source. This is voltage. And for the current will go to 0. Right, current. So when we close the switch, the current flow is there, right? The current will flow, and then the current is decreased to 0. Okay. And the charge is stored in this device. When it's the full charge, there is no current flow anymore, and the voltage becomes steady, right? So this state we call transient state. So how to get this transient characteristic? Okay, we talk about this transient characteristic. Okay, during transient, but during steady, we have learned it, right? The steady state, in steady state, capacitance and inductance will not react to the DC system, right? The capacitance will become open circuit, and the reactance is short circuit, right? It's become short circuit. Yeah. Okay. And if you remember, the characteristic of capacitance is, and the inductance L. V is L di by dt, right? And for the capacitor is I is C dV by dt, right? So d by dt is the It's make this device react to the source with transient in transient behavior here. Okay. For DC source, if we switch DC source to LC circuit, RLC circuit, you get this transient behavior. For AC, if we supply AC, you get transient AC as well. If this source is AC, if this source is, we get this graph, right? This type of graph. This is transient state, and it's steady state. Transient state and steady state. So, okay. So if we have single energy storage element, what mean by single energy storage element? It means only R or L, only L or L, only C, RL or RC circuit. For example, R and L circuit, or R and C circuit, right? This is RL, RC circuit, RL circuit or RC circuit. We will analyze this circuit in terms of first order circuit. This is the first order ordinary differential equation. First order differential equation. First order ordinary differential equation, right? Ordinary differential equation. Here. And the result may be in this shape, in decrease exponential waveform or rising exponential waveform. This is an exponential form. Okay. E minus ET, or this is maybe some value. Maybe C, right? This is CE AT 1 minus, just like this. Minus. Okay, let's see an example why we need to use differential equation to solve the circuits, right? Because the behavior of the element here, right? If we have RC circuit like this, okay, this is an RC circuit, so we can use KCL or KVL as well. KCL or KVL, but the voltage across the voltage across the capacitance is equal to VC, okay. C integrate I, right? It's integrate I. Due to IC is C dV C by dt, therefore VC is 1 by C integrate I C dt, right? Just like this, okay. So in this case, if we use KVL here, KVL, VS, right? VS is plus minus, VR plus minus here, and VC plus minus here. So VS minus VR minus VC is equal to 0, right? And if the current flow is IR here, And IR and IC are the same, right? IR is IC. IR and IC are same. Yeah. So this is Vs, and the voltage across this resistance is simple, right? It's just I into R, right? It's IR, I into R. And the voltage across the capacitance will be in the integration from, we integrate from long time back to the time t here. Okay. It's I integrate IC dt. Okay. So if we make the derivative into this equation, okay, we will get dvs by dt minus dic by dt minus 1 by c, and we dip into integrate, we have ic then equal to 0, right? Equal to 0. Or we get if we divide the equation by r and c, yeah, we get dvs by r, and then di by dt here, and then ic by rc over here. We get this equation. Okay, and we know that IR is Vs minus Vc divided by R, or the IC. Therefore, IC is C dV by dt. Okay, so we can substitute IC here by dV by dc by KCL here. Okay. So with this analysis, finally we will get the ordinary differential equation, right? For example, in this form, dV by dt dVc by dt plus 1 by RCVc equal to 1 by RCVs here, right? Then when we solve this differential equation, we will get Vc in terms of function of t here, because it's d by dt, right? dv by dt, we get the function in terms of function of t here, like this. Okay. Or we can use this equation as well. We can form the equation and we get the equation in terms of IC, and if we solve this circuit, we get IC in terms of function in terms of C also. Okay. Yeah. Okay, let's see another one example with L, R and L circuit. Okay, so this circuit we have R1 is 10 ohm, right? This is 10 ohm. R2 of 5 ohm. L is 0.1, 0.4 Henry here. Okay, so if we take KCL at this node, KCL, so we get IR1 minus IL minus IR2 equal to 0. And IR1, what is IR1? IR1, this is VL, right? The voltage of this node we call VL, or V across V, the reactant, the inductance, VL minus VS, right? Or VS minus VL divided by R1. Yeah. And this is IL. This is IL. And this is VL divided by VL divided by R2. Yeah. Okay. So we rearrange this equation Vs by R1 and VL is LdIL by dt, right here. So VL will be LdI by dt minus IL, and VL is LdI by dt divided by R2. Okay. So here we can rearrange this equation into di by dt, dIL by dt, and here IL is here, equal to R2 divided by L multiplied with R1 plus R2, or we can maybe use this method, maybe simple, Vs divided by, what is R1? R1 is 10 minus L 0.4 divided by R1 is 10, right? Minus, oh no, sorry, dIL by dt minus IL minus 0.4 by 5 dIL by dt equal to 0. Yeah. Then we rearrange into this function. Okay, this right. We can just substitute R1 L and R1 L and R2, okay, and then we rearrange into this equation, okay. And if we know Vs, we just solve for IL, okay. So with RC and RL, we need to solve the differential equation, right? So let's see some example to construct the equation. This is check your understanding, so you should do by yourself, right? Later, okay. Vs, we have C and R. So this is the final equation. So this is Vc, right? Vc is here as a function of t. This is Vr, this is Vc, and this is the voltage across T. This is I. IT will be C dV by dt, right? This is Vr. And IT and IR is equal to Vr. Okay. Or we can use KCL to this value is Vs. This is plus minus Vs minus Vc minus Vr equal to 0. And Vs is the n as a function of time minus Vc here. Vc as a function of time, and then Vr will be minus I, right? The current passed to the capacitor here into R. Then we can use I is C dV by dt, right? Vs minus Vc minus C dV by dt into R. Then we can rearrange into this equation. C dV by dt. and C dV by dt. This is current I, right? This current I. The current is the relation between current and the voltage, right? Same. And then we get this value. If we solve this, we will get the voltage across C, right? So for example, if we know R and if we know C and we know the function, maybe 10 dVc by dt plus Vc equal to Vs. Vs may be 220 cos omega t, for example. So we can get Vc, right, in terms of function of time. Okay, I leave B and C for you to get how to get into this equation and how to get into this equation. Okay, to solve the differential equation. So the differential equation, usually this type of circuit, we can get the equation in terms of voltage or current. Okay, or current. So the ordinary differential equation will be in terms of a1 dx by dt plus a0x equal to some function. Okay, equal to some function. So this those equation we can rearrange, okay, by divide the equation by a0. Okay, then we get time constant multiply with dx by dt plus x, the ks ft. Okay, this is the first order system equation here. Okay, or we call first order linear ordinary differential equation with constant coefficient. This is constant, this is constant, this is a function. Okay. Okay. For example, but if we have two energy storage, okay, our equation will become second order differential equation. It's very more difficult to solve, right? If we have L and C in the circuit, the equation become second order. Okay, I'm not going to detail with this type of circuit. Okay, just you to have some idea. If a lot of L and C in the circuit, the solution will be very complicated. Okay, for transient analysis. Okay, here this is an example. When we have L and C, when we solve this type of circuit, finally we will get second order differential equation, okay, for RLC circuit. So we focus on only RL or RC only here. Okay. Okay. So after a very long time, the circuit become steady state. When we talk about DC source, after a very long time, the circuit becomes steady state. The inductance will become short circuit. Okay, here. After when the circuit connect for a long time, we will get this circuit. Okay. Just only this circuit. Okay. For the capacitor will act as open circuit and inductor will behave as short circuit, right? Capacitor will be open circuit and the inductor will behave as short circuit. Okay. Yeah. When we switch on, when we close the switch, so after a long time, this become open circuit. Okay, the circuit become open circuit. when we solve the circuit with C and L after a long time. But when the switch just closed before go to steady state, so we can analyze by ordinary differential equation. Okay. And for the inductance, it's become short circuit, right? When the switch change for a long time. Okay. Okay. I will take this example for you. So if the switch is open for a very long time, has been open for a long time, find the current flow when the switch closed. Okay. If the circuit is being like this for a long time and then we close the switch at time t0. Okay, what happened to this circuit? So when the switch is closed, okay, we can take KVL for this circuit, right? KVL for this circuit. So 40, this is V, okay, V source, okay, or VT here, right? V source T, V source T equal to how much voltage? LdI by dt, right? This is plus, minus, this is plus, minus, V source minus LdI by dt, and minus I, right? Current flow I, and then we solve for I, okay, equal to 0. So we can write down this equation, right? R is 10, L is 2, and V is just 40. Okay. So we arrange this equation, we get di by dt, right? Plus 5I equal to 20 here. So we solve for I. How to solve for I, right? For this simple equation, we rearrange this equation. Then we get dt. It's just like we solve dy by dx plus 5y equal to 20, right? Have you ever solved this type of equation? I think, right? And then, but we get y equal to fx, right? In this case. So in this case, we try to get I as a function of t, right? Yeah, just similar. Okay. So to solve this type of equation, di, we just rearrange like this. Di by dt equal to 20 minus 5I, and then we just separate di and dt, right? And then we make integration this equation, right? So to integrate di by 20 minus 5I, we get ln of 20 minus 5I, and then minus 1 divided by 5, right? And in the right hand side integrate dt, we get t plus c1, right? We get t plus c1, okay, just like this. And this is a solution of current, right? Then I try to rearrange I as a function of t. So we will get ln of 20 minus 5I equal to minus 5, right? Minus 5 into t plus c1, okay. So at this moment, we don't know what is c1. We don't know yet, right? This c1. Then 20 minus 5I will be e power minus 5 t plus c1, like this. Therefore, I will be e minus power minus 5 t plus c1, and then how much? Minus, right? Minus here and plus 20, right? This is 5i. We move 5i here and e here. So e minus e power 5 plus 20, right? E 5i, right? So I equal to I is 1 by 5 minus 1 by 5 e power minus 5 t plus c1 plus 4, right? Plus 4. So we rearrange this term. So it's into e power minus 5 t, and this is e minus 5 c1, right? And it's minus 1 by 5. So this is constant, right? This term and this term, right? And plus 4. So this term we can represent this term as one constant, right? C, okay, any C, right? So I equal to any C that we don't know yet what is C into e power minus 5t plus 4, okay. Yeah. This is the characteristic of the current. When switch is closed, the current will be flow with this function. Okay, the current will flow in this function. And what we know that at t is 0, the current is 0 because it has been open for a long time. So at t equal to 0, current start from 0. So the current start from 0 at t0, right? At t0. Therefore, this is 1, right? So we can solve for C is 4. So finally, the current will flow in this form. When we close the switch, the current will flow in this form. So when I equal to minus 4e power 5t plus 4. When t is 0, current is 0, right? Here. But when t go to steady state, what is the current? This term will go to 0, right? This term go to 0. I go to 4, right? So this is the exponential increment of exponential. So when we, therefore, this solution represent that when we close the switch, the current start increase, right, into 4, and after that it remain 4, right? It remain 4. What mean by it remain 4? It means that the inductance become short circuit. If the inductance is short circuit, the current is 4, right? The current is 4, right? So this solution is correct, right? Because when we close the switch for a long time, it's 4 amp, right? It's 4 amp. But during transient state, it's increased by this characteristic, right? With this time constant. Okay. So this is how to solve this type of transient circuit by differential equation. So you need to solve differential equation. Okay? But it's not very difficult if the source is DC. If the source is DC, right? And the circuit have only single storage device, only L or only C. Okay. Any question so far? So another way to solve this type of circuit is to separate this equation into natural response and forced response, right? For natural response, we leave this side to 0, right? With this side 0, we can just solve for I. I natural response is minus C e power 5 here, right? And for forced response, we put this term 0, and then we get I at t go to infinity is 4. We get I is 4. So we plus this together, we get this solution. Okay. Or you integrate this equation, we get the same thing, right? We get the same thing. So you have to learn how to solve with this method. No, in mathematics, calculus, right? In calculus, we solve by this method. Then you get final solution like this, and then we take initial condition at t0, I is 0. So at t0, I is 0. We solve for c, we get c here, right? Then we get c, we get this equation as well. Okay, this is how to solve transient response of first order circuit. Okay. When switching is steady, right? We solve for transient behavior of the circuit. Okay, I think that's this is I have explained by that equation already. Let's depend how to get is the difficulty is how to get the equation to solve first, right? How to get the equation, how to construct the equation of the circuit by KVL or KCL that we have learned before midterm, right? Okay. Then we will get this type of equation to solve. We can separate into natural response and forced response, or we can just rearrange it and make the integration, right? Rearrange and into this is maybe only di or only dv or only dt, and then we integrate two sides of the equation and we get the solution. Okay. Yeah. So the natural response is we keep the right hand side to 0, right? And then we get this natural response. And for forced response, we just get for this equation, right? With time t into infinity, there's no change anymore. What happened when no change? Okay, when d by dt is 0, right? Nothing changed. That's what happened for forced response. You get this. Okay, this plus is together, right? The solution will be natural response and forced response plus together. Okay, plus together. Okay, you get a complete response as a solution. Okay. And so we have time for this example. Okay. Okay. Okay, with this example, we have Vc is 0 at time 0. If the switch closes at time 0. Okay. And switch close, when the switch close, Vc is 5 volt before switch close, okay? Before switch close, Vc is 5 volt. In this case, right, it's not 0. So there is some charge stored in the capacitor here, right? And the resistance is 1 k ohm, and the capacitance is 470 microfarad. And Vb is 12, then we close the switch. Okay, because When we close the switch at t before 0, Vc is 5 ohm. Okay, so Vc at time 0 is, 5 volt, is 5 volt. Okay, and when the switch closed for a long time, it should become 12, so we can guess that Vc is 5 ohm before the switch closed, right? And when the switch closed, it will reach to 12 volt, right? And after steady state, Vc become open circuit, and the voltage here is 12 volt, right? It will be come to 12 volt. So we can guess the waveform of Vc should be maybe like this, right? Okay, let's go to 12 volt. There's some exponential 12, yeah. Right. So when the switch is closed, we can take KVL. So VB, this is plus minus, this is plus minus, VB minus VR, right? And VC, and then minus VC here, equal to 0. And what is IC? IC is C dV by dt. We substitute IC, right? Because the current flow here is IC. It's C dV by dt. So we can construct this equation, right? Then VB minus RC dV C by dt minus VC. So we solve for VC, right? Right? But we can guess here that VC will be in this form, right? Here. So we solve for VC. So we rearrange this equation, we get RC dVC by dt plus VC equal to VB. Or we can substitute RC. What is R? R is 1K, right? 1K into 470 micro, 470 micro dVc by dt plus Vc equal to VB 12. Okay. We solve this equation, right? So with any method you prefer, right? This equation to get what is Vc, right? Okay, we get Vc as a function of time. So in this example, we solve it by take this time constant as RC, right? Forced response and natural response. We can just substitute the final formula. We get this equation. Right? Xt would be Vc, right? Xt will be Vc, and the time constant would be RC. Yeah. This is just instant formula to solve this type of equation. Ks is 1, right? Ks would be here. And VB is 12 here. Okay. So therefore Vc is Vc at steady state plus Vc as initial condition minus Vc steady state is steady. This is initial. This is steady, right? And this is time constant. Time constant is this term, right? This is time constant. Then we just substitute. When steady state Vc is 12, at initial condition it's 5, steady state is 12, and time constant is here, right? So this is Vc. Then this is steady state response is 12, and the transient response is here, right? When t approach to infinity, so this term approach to 0, we get 12 here. Okay. Or we can just rearrange this. Maybe in general form is maybe 1, 7, 1, 7. minus 12 e into minus t by 0.47, just like this. Okay. At t0, Vc is 5, right? As t infinity, Vc is at t infinity, this is 12, right? Oh, sorry, 5 is over here. This is 7, right? 7. No, minus 7. Five minus 12, right? Minus 7, right? No. How much? 5 minus? Oh, this is sorry. Yeah, I'm so confusing. 12, right? 12 minus 7, right? Just like this. When t is 0, this is 5. And when t is infinity, this is 12, right? This is approach to 7 and approach to 0, right? When t is 0, this is 7, right? When t is infinity, this is 0, right? So just like this. Okay. Or you can follow this as well. The same thing, right? Just different explanation, right? Okay, this is when we plot Vc, right? When we plot Vc. Earlier we can guess the graph of Vc, right? The response of Vc is this term, right? But if we plot only natural response, forced response, only natural response is like this. We put the term of forced response, we get this. Okay, this will be your another homework. Okay. So we have 2 homework, right? Maybe next week is okay for you, right? Okay, so we have homework. So next week we talk about diode, right? Diode. So next slide. Okay. Any question? So I should stop here, right? So, but last time I take the time of another class. Okay. So if no question, so see you next week.